All right, let's talk about kinetic molecular theory. Kinetic molecular theory allows us to explain the behavior of gases using basic ideas from physics, okay, apply them to the movement of atoms and molecules. So these basic ideas are Newton's second law, which says that force equals mass times acceleration. Newton's third law, for every action there's an equal and opposite reaction. And we're also going to apply the idea of kinetic energy being equal to 1/2 times the mass times the square of the speed. So we're going to apply these to atoms and molecules, and we can see that we can use this to explain the ideal gas law. Okay? So, what are the assumptions that we make to explain ideal gas behavior? First of all, we assume that gas particles, okay, are point masses that are in continuous random motion. Now, point masses means that they occupy a negligible amount of space. So we're ignoring that they have finite volume. Okay, and this is an assumption that becomes valid when we're dealing with gases at very low pressure. More and more valid at lower pressures, because then the volume of the container will be so much bigger compared to the actual volume of the gas molecules themselves. Okay, continuous random motion. Evidence of that, okay, is known as the experimental basis for that assumption is the phenomenon known as Brownian motion. Brownian motion refers to movement of small particles that we can actually see through a microscope that appears to be random. And the explanation for why this motion is random is because these particles that we could see through a microscope are actually constantly being bombarded by molecules that we can't see. Okay, so there's a couple of videos that you might want to look at on YouTube to explain Brownian motion. Let me see if I can pull those out for you. Right here, this video called Molecules in Motion. I put a link to this in the Moodle course site. Okay, and here's another one on Brownian motion that you can look at. Okay. So the basic idea there is these particles that we might be able to see through, little tiny particles, but we might be able to see through a microscope. They're sort of random motion that we see from these particles can be explained in terms of collisions with particles that we can't see, and those are your molecules. All right. So there's no energy that transfer. We also assume that there's no energy transfer that occurs when gas particles collide with the walls or with each other. So we say in physics that the collisions are elastic. Although this is not really, strictly speaking, valid for individual collisions, but if you do average it out over all the gazillions of collisions that's happening within a sample of gas, then we can the total energy transfer for all these collisions does average out to zero. So for simplicity, in applying the physics to our collisions, we can make that assumption, okay, and arrive at an expression that will allow us to explain ideal gas behavior. We're also going to assume that the gas particles exert no force on each other. That's not true, but in the limit of situations where the ideal gas law is valid, okay, we're saying that the molecules in an ideal gas, particles, are so far apart that for practical purposes, we can, the assumption that they exert no force on each other should be valid. Okay, and we'll see in a later lesson when we talk about real gas behavior, then that we can actually make corrections for the fact that this is not strictly correct. But we're trying to explain ideal behavior here. All right. So how do we interpret the idea of pressure? Pressure of a gas is due to collisions of particles with the walls of the container. So if this is the wall of your container, your collision of a particle with a wall would impart a force on it. Okay? So, if you recall, acceleration is a change in velocity. So if a molecule collides, okay, let's just say it's colliding head-on with a wall, and then so it's going forward, and then once it collides, it moves back in the opposite direction. That's a change in speed, okay? Not change in speed, change in velocity, change in the direction, even though it doesn't change speed, because we're assuming that there is no energy transfer. So the kinetic energy, 1/2 mv squared, remains the same before and after the collision. Okay, but there is acceleration because it's changing velocity, it's changing direction. the fact that it's changed direction, that means that there's a force. The wall is exerting a force on the um, on the molecule or the atom that collided with the wall. Okay, so the wall exerts a force on the particle. The force is mass times the acceleration of the particle. Okay, the particle also exerts a wall on the force according to the third law. If the wall is exerting a force on the particle to cause it to change direction, and that means the particle itself is also exerting a force on the wall. That's the third law, Newton's third law. Okay, so the pressure due to the particle, okay, is given by F over A. That's the force that the particle exerts on the wall divided by the area. So pressure is defined as force per unit area. So if you have tons of lots of these particles, gas particles in your sample, there's going to be a lot of collisions against the wall. And so if you add up all those forces, divide by the total area of the wall, you get the pressure on the wall. Okay? So let me just see if I can give you a way to visualize what pressure is. There's some really nice animations that you can look at. Let me pull that up for you. Gas properties right here. Here's a simple animation from Oklahoma State University. Here you have a molecular representation of a gas sample. Notice that they're very far apart. They're more or less free to move. And so what happens here is the collisions of the molecules against the wall exert a pressure on the wall. Okay? Here's another one. This animation right here is Java applet. It's more interactive, also interactive. We can make manipulations of it, of the movements. So you can try to correlate pressure, temperature, and volume with the relationship between those two with the behavior of the molecule. We're going to come back to that in just a short while. Okay? So anyway, let's look at this example. Let's say you have one nitrogen molecule, okay, and the mass for each N2 molecule will be a very small mass, 4.65 times 10 to the negative 26 kilograms. How do you get that number? If you recall, N2 is 28 atomic mass units, right? So that is for 1 mole. So if you divide that by Avogadro's number, it's 28 grams divided by 6.02 times 10 to the 23rd. So this is grams per mole, right? Divided by 6.02 times 10 to the 23rd molecules per mole. That gives you grams per molecule, and you change that to kilograms, you should get 4.65 times 10 to the negative 26 kilograms. So let's say you have a nitrogen molecule moving at constant speed of 300 meters per second. It collides with a wall, and then once it collides with the wall, reverses direction. Let's say this happens during a 1 second time frame, and let's say the area of the wall is 10 square centimeters. Okay, so I mean constant speed remains the same, it's just changing direction. What will be the pressure on the wall due to this one particle? So we say, okay, the force equals mass times acceleration, and our mass is how much? 4.65 times 10 to the negative 26 kilograms, and our acceleration is the final speed, which is what's the speed? 300 meters per second. So final velocity would be, we're going to take this direction as the positive direction and the opposite direction is negative. So your final velocity is going to be negative 3, it's going in negative direction. So negative 300 meters per second minus the initial velocity is positive 300 meters per second. Okay, divided by the elapsed time of 1 second, 1.0 second. Okay, so that's your acceleration. Change in velocity over change in time. That's the average acceleration during that 1 second time period. So this is going to be this kilograms right here. So the force would be 4.65 times 10 to the negative 26 kilograms times the change in speed. The final is negative 300. That's negative. Minus 300 is positive 300 is the initial velocity. So that's change in velocity is negative 600 meters per second divided by 1. So that gives us this one. Change that to scientific notation. That's 2.79 times 10 to the negative 23rd. Okay. Kilogram meters per second squared, so that's a Newton. So divided by the area, that's the force. Okay, you'll notice it's negative because that's the force on the particle, but the force on the wall would be the opposite direction. We're just going to take the absolute value. So pressure due to this one molecule is force divided by area. So it's 2.79 times 10 to the negative 23 newtons. And our area is 10 square centimeters. Okay. So 10. A centimeter is a 10 to the negative 2 meter. So this is a centimeter squared. So this one is a centimeter, right? So that's what centimeter squared is. So this gives us that. Let's just take an absolute value for that one. Oops, what happened? Let's try that again. 2.79 times 10 to the negative 23rd divided by the area, which is, okay, this is, let me do this manually. This is 10 times 10 to the negative 4 in the denominator. So divided by 10 times 10 to the negative 4. And that gives me 2.7 times 10 to the negative 20. 2.79 times 10 to the negative 20 newtons per square meter. A newton per square meter is called a Pascal in SI. So that's what the pressure is due to one molecule. Of course, with dealing with moles, generally we're going to be dealing with way more than just one molecule. Okay, so the pressure, this is, you'll notice this is a very small number. But that's the idea behind pressure. It's due to collisions of atoms and molecules with the wall, which causes them to part a force. Okay. Now, if you have lots of particles, okay, moving in 3 dimensions, then it can be shown that the pressure would be equal to 2/3 times the sum of all the translational kinetic energy divided by the volume. Okay, so sum of all the translational kinetic energies. What do we mean by translational kinetic energy? That's 1/2 mv squared. Okay, kinetic energy we say is 1/2 mv squared. When we talk about that in general, we mean the translational kinetic energy. I'm specifying translational kinetic energy here because a molecule can actually have more than just translational kinetic energy. So what we call the kinetic energy of the molecule is the sum of a translational energy and energy due to rotation and vibration. If you want to see, let me show you an animation that shows you the additional kinetic energy due to motion of the molecules. This is an old movie that you can find at the Internet Archive, archive.org. Okay, just do a search for Molecular Motion, 2nd edition. When you get to at the 5:51 mark, there's an animation there that shows you the differences between translational motion, rotational motion, and vibrational motions. So translational motion, as you'll see here, is described as motion from place to place, okay? Motion through space. And then rotational motion would be sort of like the tumbling motion of the molecules. And then within the molecule itself, you'll have what are known as vibrational motions. So let me just play that segment of the video. This is a very interesting video and very educational. You should really watch it. I have a link to this in the Moodle course site, okay?
Here in very slow motion are models of several kinds of gaseous molecules undergoing translation, that is, motion from place to place. In addition, most of the polyatomic molecules have a further kind of motion, rotation. And close examination shows still another kind of motion, vibration. Rotation and translation involve only molecular tumbling and simple motions through space. But vibrational motions can appear complicated, as in this model.
Okay, that should be enough. All right, so anyway, what we call translational kinetic energy is kinetic energy that's associated with motion, simple motion through space. Okay, that doesn't include the total kinetic energy for a molecule has to include not just translational motion, but rotational kinetic energy to the tumbling. You can say tumbling motion of the molecule, and you have rotational, and you have energy due to the vibration. I mean, kinetic energy due to the vibration of the atoms within the molecule. Okay. So anyway, if you compare this equation right here, this is something you can derive from, like I said, applying physics to a collection of molecules. So we can calculate the pressure that they would depart on the wall. Okay, it's related to their translational kinetic energy. Let's compare this equation with the ideal gas equation, which says P is equal to nRT over V. Remember, ideal gas law says PV equals nRT. So if you compare these two, you can see that you can solve for the sum of the translational energies, okay? And it should be a simple matter of showing that when you solve for the sum of the translational kinetic energies, it's going to be equal to 3/2 times N times R times T. So this equation then gives us now a way of interpreting what temperature is, okay? So what's temperature? You can see it's related to the translational energy. And you'll notice if you divide this by the number of moles, okay? Let's see. If you divide both sides by the number of moles, okay, you can see temperature is sort of like it's like averaging your translational kinetic energy, right? The total divided by the actual number of molecules. So temperature, then, we say, is a measure of the average kinetic energy, average translational kinetic energy of the molecules, okay? So temperature is a measure of the average translational kinetic energy. So total energy divided by number of moles, that gives you 3/2 RT. This is the translational energy of 1 mole of molecules, okay? So that's per mole. So if you divide that by Avogadro's number, okay, you can see 3/2 times kT. K is R divided by Avogadro's number. That's called the Boltzmann's constant. And so the average translational kinetic energy, that's per molecule, is 3/2 kT. So temperature is, you say, 2/3 times K, 2/3. We solve for T here, you can say temperature is 2/3 K times the average translational kinetic energy. So that means the higher the average kinetic energies of the molecules, the higher the temperature. Okay, and as I've mentioned, there's molecules do have additional kinetic energies due to vibration and rotation, whereas atoms only have translational kinetic energy. So here's a question. Which has more kinetic energy? A molecule with a mass of 32 atomic mass units moving at 300 meters per second, or that's a molecule, or an atom with a mass of 32 atomic mass units, same mass, moving at 300 meters per second. Which one has more kinetic energy? The answer is A. Why? Because they have the same translational kinetic energy. going to be the same, right? But the molecule has extra energy. Translational kinetic energy plus rotational kinetic energy plus vibrational kinetic energy. So we say the molecule would have more kinetic energy total. In terms of just translational energy, just movement from place to place, simple movement from place to place, they have the same translational kinetic energy because they have the same mass, the same speed. Okay? So let's calculate the translational kinetic energy per mole of gas particles at room temperature. What was the formula? Yeah, translational kinetic energy is 3/2 nRT. That's the total. So per mole, that would give you 1 mole for N right there. So 3/2 times 1 mole. Okay. Times R, which is 8.314 joules per Kelvin per mole. That's the value of R. Joules per Kelvin per mole. And the temperature is 298 Kelvin. So Kelvin cancels out, mole cancels out. That gives you the translational kinetic energy in joules of 1 mole. So let's solve for that. 3/2. 3 divided by 2 is 1.5. Make this in regular notation. Times 8.314 times the temperature of 298. That's 3,716 joules. Okay. Let me do this. I'm going to calculate RT first because this is something you'll see a lot. Okay, so 8.314 times 298. That's 2477. Okay, so that's going to be 2.48. If you're doing 3 sig figs, 2.48 kilojoules. This is 2.48 kilojoules per mole. Okay, so multiply that by 3/2 and 1 mole. That would be equal to times 3 divided by 2 times 1.5, so that's going to be 3.72 kilojoules per mole. Okay. Try to remember this number because you'll see that a lot. That's the value of RT at room temperature. And there's a lot of formulas that you'll encounter that has RT in it, so it's a good number to remember. It's about 2.5 kilojoules per mole. Okay, so 1.5 times that would be your translational kinetic energy per mole. That's the total kinetic energy of 1 mole of gas molecules. So which sample of gas has more translational kinetic energy at 298 Kelvin? 2 moles of neon, 1 mole of H2, or is it the same for both? Let's see. What's a formula for translational kinetic energy? It's 3/2 nRT, right? We're just dealing with translational kinetic energy here. So same temperature. This is n equals 2. This is n equals 1. So which one has more translational kinetic energy? Neon will have more translational kinetic energy. Okay? Bigger n. Same T, same RT, same 3/2 here. So bigger the n, the more translational kinetic energy. How about this question? Which sample has more translational kinetic energy per mole? So it doesn't matter how many moles you're given. You just compare 1 mole. You're really just being asked to compare 1 mole versus 1 mole. So translational kinetic energy per mole is 3/2 nRT divided by n if you want it per mole. So it doesn't matter what n is, right? So that n cancels out. So 3/2 RT is the translational kinetic energy per mole. Since we're looking at the same temperature, same T, per mole value of translational kinetic energy would be the same. let's calculate the average kinetic energy of helium atoms at 300 Kelvin. So kinetic energy is 3/2 nRT. That's a total, right? If you want per mole, you divide by number of moles, right? Will give you per mole. If you want per atom, you divide by Avogadro's number. Okay, that will give you the average kinetic energy. So I'm going to put this in this bracket symbol right here to say that's the average kinetic energy per atom. Now, R over Avogadro's number is also known as Boltzmann's constant. So if you remember, we said the formula for that is 3/2 kT, or K sub ET. Right? So let's plug in the numbers. 3/2. R is 8.314 joules per Kelvin per mole, divided times the temperature of 300 Kelvin. Let's just treat that as exact. And our Avogadro's number is 6.022 times 10 to the 23rd per mole, atoms per mole. So per mole cancels out, Kelvin cancels out. That gives you the answer in joules. Okay? So that would be how much? So plug in those numbers. Let's see. If you remember, RT was about 2.5 kilojoules at room temperature, right? So you could do it that way and then divide by Avogadro's number. So this is about 2,500 joules in the numerator. Let's see, 8.314 times 300. You can see the numerator is about 2,500 joules. It's about 2.5 kilojoules. Okay, divided by 6.02 times 10 to the 23rd. That's this number right here. So 4.1 times 10 to the negative 21. So 3/2 times 4.1. 4 times 10 to the negative 21. Divide that by 1.5. That gives you 6.21 times 10 to the negative 21 joules. Okay? So that's kind of a small number in joules. That's of course because you're dealing with energy on a per atom basis. So single atom's not going to have much energy. All right. Which sample has a higher average kinetic energy? 2 moles of helium at 298 Kelvin, a mole of O2 at 298 Kelvin. So you're talking about average, so that means on a per atom or per molecule basis. So this is on a per particle basis. So average translational kinetic energy would just be 3/2 kT. It doesn't matter how many you have, you can ignore how many moles you have, right? Because you're talking about an average. Talk about an average, you just divide by however many you have. So ignore how many moles you have. So really just comparing helium and O2. They're going to have the same translational kinetic energy because they have the same temperature. So which one has the higher average kinetic energy? They have the same translational kinetic energy, okay? But O2, okay, so they're going to have the same average translational kinetic energy, but O2 has, in addition to translational kinetic energy, rotational and vibrational kinetic energy, because that's a molecule. Whereas helium is an atom, it won't have vibration and kinetic. It will not have vibrational and rotational kinetic energy. So the answer would be B. Okay? Now, for a collection of particles with the same mass at a given temperature, okay, we can show the following. Okay, first of all, translational kinetic energy we say is K 1/2 times the mass times the square of the speed, right? And we've already shown that the average translational kinetic energy is 3/2 kT, where K is Boltzmann's constant. So if you have a collection of these particles, okay, then your 3/2 kT would be equal to 1/2 times mass times the average of the square of the speed. Why is that? Let's see. If we say the average kinetic energy is 3/2 kT, right? Case of dt. That is 1/2 mv1 squared plus 1/2 mv2 squared plus 1/2 mv3 squared, and so on, right? Divided by the total number of molecules. Well, this is going to be 1/2. I can factor 1/2 m. They all have the same mass. v1 squared plus v2 squared plus v3 squared, and so on, divided by the total number of molecules. So that is just going to be equal to 1/2 times the mass times the average of the v squared, the average of the square of the speeds. Okay? So you add up all the squares of the speeds divided by the number of molecules. That gives you the average of the square of the speed. All right. So the average of the square of the speed, then, you can solve for that. It's 3/2 kT divided by 1/2 m, right? So what would that be? This is going to be 3/2 kT divided by 1/2 m. So you can see your 2 cancels out. So that just gives you 3 kT divided by m. And kT, if you recall, is just r divided by Boltzmann's constant, if you recall. It's just r divided by Avogadro's number. And the mass of one molecule is the mass of 1 mole. So big M sub m here is just the molar mass. Okay, it's molar mass. So if you take the molar mass divided by the Avogadro's number, that gives you the mass of 1 molecule. So this little m right here, the mass of 1 molecule, is the mass of 1 mole divided by Avogadro's number. So if you make that substitution, what do we see? Avogadro's number cancels out, right? So the average of the square of the speed is just 3RT divided by the molar mass. Okay? So from this, we can take the square root. Take the square root of this. So that's the square root of the average of the square of the speeds. You get what is known as the root mean square speed. So it's going to be equal to square root of 3r square root of this thing right here. So square root of 3RT over the molar mass. So that's called your root mean square speed, RMS. Okay? Root of the mean of the square. The mean of the squares is the average of the squares, and root means you take the square root of it. So the RMS speed, as you can see, is directly proportional to, okay, the square root of the temperature, okay, and inversely proportional to the square root of the molar mass. That means the higher the temperature, the higher the average speed. You can think of RMS speed as sort of like an average speed. Okay, it's not really a true average speed. It's the square root of the average of the square of the speed. Okay, but still, it's going to be related to the average speed. It's the higher that value is, the higher the average speed is. So that we can say the average speed. Let me just think of it as average speed for now. Is directly proportional to the square root of the temperature. So the higher the temperature, the higher the average speed. The higher the molar mass, the heavier the molecules are. Okay, you have an inverse relationship here. This one's in the denominator. The higher the molar mass, the lower, for the same temperature, the lower the average speed. Okay, so that's what that equation means. So like I said, RMS speed is sort of like an average speed. The true average speed is actually just slightly smaller than this, but it can also be shown to be directly proportional to the square root of the temperature and inversely proportional to the square root of the molar mass. In fact, so if this is the formula for the root mean square speed, you can actually show, and we're not going to do it at this level, but in a higher level class, you'll show physical chemistry. You can show that the average speed is equal to 8RT over pi times the molar mass. And 8 over pi is just 2.5465. Okay. Let's see. 8 divided by pi. See, that's 2.5465. Okay. Compare that to the formula for the root mean square speed. The only difference is this 3 right here and this 2.5465. So your average speed is slightly larger than your root mean square speed. Okay? But the higher the root mean square speed, the higher the temperature, the higher the average speed, the higher the root mean square speed. And for the same temperature, the heavier your molecules are, the slower their average speed is. So let's apply those ideas to this question. Which gas sample has particles with the slowest average speed? Is it 2 moles of helium at 298 Kelvin, 1 mole of helium at 500 Kelvin, or 2 moles of O2 at 298 Kelvin? So what's our formula for average speed? It's directly proportional to the square root of temperature, inversely proportional to the square root of the molar mass. Okay, let's write molar mass this way, m sub n. So let's compare then temperatures. Okay, so notice that it doesn't matter how much you have. Again, anytime you're comparing averages, it doesn't matter how much you have. So temperature 298 Kelvin versus 298 Kelvin, helium versus O2. So let's compare A and C. Which one has a bigger molar mass? Molar mass O2 is larger than helium, right? So you've got a bigger denominator for O2. So the heavier oxygen molecules would have what? Would be more sluggish, you'd say. It would be smaller for larger molar mass. So it would be slower for O2. Okay, so O2 would be slower than helium, so you can cross this one out. Okay. What about helium? O2 at 500K versus O2 at 500K. Okay, you've got different molar masses, different temperatures. You can't make a direct comparison. So let's compare A and B instead. What happens between A and B? So we've already compared A and C, right? And we said it can't be A. Let's compare A and B then. Well, let's see. We're comparing helium. Again, doesn't matter how much you have. So helium at 298 Kelvin versus helium at 500 Kelvin. So which one has a higher speed? Higher temperature, higher average speed. So we say helium would have a higher speed. Okay, so at 500K than 298K, so it can't be B either. So the correct answer here is oxygen at 298 Kelvin. Okay, so summarize. Compare these two. The lower temperature would have a lower speed. Compare these two. The heavier mass would have a lower speed. So the answer is C. Let's actually calculate the average speed of O2 molecules at 298 Kelvin. So the average speed, square root of 8 RT over pi times the molar mass. Let's do this calculation because you have to, I want to give this specific example because I want to show you how the units work out. Okay, so this is going to be equal to 8 times. The best way to do this is put everything in the base SI units. So 8.314 joules per Kelvin per mole. And our temperature is 298 Kelvin divided by pi, which is million. Molar mass of O2 is 32 grams per mole. Okay? But you have to put that in kilograms. Okay? So 32.00 times, so let's put that in grams first, grams per mole. You have to change your grams to kilograms, so there's 1 kilogram in 1,000 grams. Okay, So grams cancels out. Moles cancel out. Let's look at the unit inside, okay? Kelvin cancels out. So what's the remaining unit? The remaining unit inside your square root sign is joules per kilogram. What's a joule per kilogram? A joule is a Newton meter, right? Force times distance is joules over a kilogram. A Newton is a unit of force. So force is mass times acceleration. So that would be a kilogram. Acceleration is meters per second. So meters per second squared. That's a Newton, okay? And times a meter over kilograms. Your kilogram cancels out. So what do you have left inside in terms of base units? The unit inside is going to be meters squared per second squared. And if you take the square root of that, okay, the unit that comes out will be meters per second. So let's plug in all these numbers. 8 times 8.314 times 298 divided by pi divided by 32 and divided by 1 over 1,000, so you multiply by 1,000 times 1,000, and that gives you 1.97 times 10 to the 5th, and then take the square root of that. So inverse, oops, I don't have a square root thing here, so I'm going to raise it to the power 0.5. That makes it a square root equals, that's 4.44 times 10 to the 2. So in regular notation, that's 444. Okay? So this is 444 meters per second. That's the average speed of oxygen molecules at room temperature, on average. Okay? Now, let's take a look at some of the gas laws that we've seen before and see how we can interpret it in terms of kinetic molecular theory. Boyle's law, if you remember, says at constant temperature, a smaller volume would mean a higher pressure, a bigger volume would mean a lower pressure, right? Pressure and volume are inversely proportional, so PV is a constant at a given temperature. So how do we explain this in terms of kinetic molecular theory? Well, think of it this way. If your volume is smaller, then your molecules will have less distance to travel between collisions, okay? And so they're going to have more frequent collisions with the walls, then that would lead to higher pressure, which is what we observe, okay? Hamilton's law. Hamilton's law says that for a given volume, pressure is directly proportional to temperature. The higher the temperature, the higher the pressure. Well, how do we explain that? Well, if you look at a fixed volume, okay, if you have higher temperature, you're going to have faster speed, okay? Faster speed then would mean more frequent collisions with the walls, and because the acceleration will also be larger, because you have V final minus V initial, the magnitude of the velocities would be larger, you're going to have more force exerted on the wall. Not only are you going to have more frequent collisions with the walls, each collision is going to exert a stronger force on the wall that would lead to higher pressure. And Charles' law, how do we explain that? Well, first we look at Hamilton's law. We say that the higher temperature would lead to higher pressure, right? So if you want to maintain the same pressure, then we're going to have to increase the volume to reduce the collision frequency. So that would explain Charles' law. Avogadro's law, same temperature and pressure, volume is directly proportional to the number of moles. Okay? How do we explain that using kinetic molecular theory? Well, more particles you have, the more collisions with the wall. Okay? So if you want, say if you have a fixed volume container, okay, the number of moles will be directly proportional to the pressure. If you want to so if you increase moles, pressure has to increase. If you want to maintain the pressure, you'll have to make your container bigger, okay, to maintain that pressure. Let me show you some animations that will help you visualize this. Right here, this PHET simulation in Colorado, phet.colorado.edu. Look for gas properties when you go to that website. Okay, you'll find it under, if you go to the home page there, play with sims, look under chemistry, and under chemistry, general chemistry, you'll find, where is it? Gas properties. Right here. Okay, and if you run that simulation, I've already gotten that running here. This is what it looks like. Okay, so let's see what happens if, let's say, we wanted to maintain, we can move things around. So let's say I want to fix my temperature, okay? And I'm going to see how pressure and volume are affected. So I'm going to change my volume. What happens? Okay, so fixed temperature, 133 Kelvin. The pressure is 0.23 atmospheres. If I were to squeeze this, what's going to happen? Look at the, okay? You'll notice the temperature goes up, okay? But since I want my temperature to remain fixed, okay, I'll wait for it to come back down. So once it's come back down, look at what happened to the pressure now. It's higher. Let's do that again, okay? So our pressure right now is 0.24, right? By pushing this in, I'm actually transferring energy to my atom, so the temperature is going to go up, okay? And so what's going to happen is I have to wait a while for the temperature to come back to what I want, since I want my temperature constant before I check my pressure again. So my pressure right now is 0.24, 0.25, okay? So I'm going to change my volume, but once the temperature settles back to the temperature that I wanted, the same original temperature, look at what my pressure is. My pressure is higher. And why is that? The reason for that is the molecules have less distance to travel in between collisions with the walls. You have more frequent collisions with the walls. They get less to travel. So that's higher pressure. If I increase the volume, what happens to my pressure? It drops, because you now have less frequent collisions with the wall. Let's see what happens if I were to fix the volume this time. Okay, I'm going to fix the volume, and I'm going to heat my gas. So if I heat my gas, the temperature increases. Look at what's happening to the pressure. The pressure has gone up. Okay, because your molecules are moving faster, there's more frequent collisions with the walls. Not only is the collisions more frequent, but they're moving at faster speeds when they collide with the wall, so they impart more force. What happens if I cool it down? Lower the temperature. Look at what happens to this pressure when the temperature goes down. Pressure drops, and look at what's happening to your molecules. They're moving less. Okay, they're moving more slowly. Okay, so the frequency of the collisions with the wall is lowered. Okay, less frequent collisions, less energetic collisions, we also say, because they're not moving as fast, so they're imparting less pressure, less force on the wall, so the pressure kind of goes down. Alright, so that's how you can explain the gas laws in terms of the behavior of molecules. Alright, so that's a good website to go to. It's a good animation to play with. Here's another one at Oklahoma State. Okay, intro.chem.okState.edu/13114F00/laboratory/glp.htm. So here you have is an animation. Okay, you'll notice that this is a pressure of 1 atmosphere, 22.4 liters. What would happen if I were to shrink the volume without changing the temperature? Shrink the volume, the pressure goes up, you have more frequent collisions with the walls. Increase the volume, they have more to travel, less frequent collisions with the wall. You see the pressure goes down. Okay, and so this is just another animation you can play with. And the nice thing about this animation right here, it also shows you the distribution of the speeds of the molecules. Remember, we talk about average speed. One thing you have to realize is not every molecule will have the same speed. Every time they collide, the energy actually does get transferred from one molecule to another. But overall, if you are dealing with a system that has a fixed temperature, it has total energy, fixed total energy, then that means that the sum of all the energy transfers is going to end up being zero. Okay, so there's a no net transfer of energy overall for the entire system. So let me see. Another website that you might find useful, we'll talk about this in a little while, distribution of speeds. I think that's the next topic. Okay. Like I said, particles do not all move at the same speed at a given temperature. Okay, this equation right here, this is called the Maxwell speed distribution, tells you the how the molecular speeds are distributed at a given temperature. You'll notice this F is a function of speed, okay, and this is mass, it's over 2 pi, Boltzmann's constant, there's temperature right here, right? And so if you plot that versus speed, okay, F versus speed, this is the graph that you look at, that you see, okay. Now, where this function is at a maximum, the peak in this function occurs at the temperature, at the speed where this function is at a maximum is what you would call your most probable speed. And your most probable speed you can show from this equation using calculus would be equal to square root of 2 RT over m. So the most probable speed you'll see is related to the average speed, which was square root of 8 RT over pi times the molar mass. Okay, and from this you can also get using calculus, you can get the expression for this average speed. Okay, so this is the distribution of the speeds. The way you would interpret this graph is if you calculate the total area under this graph. Okay, the total area is 1. So for any, let me see, I think I got the next line on that one. Okay, the total area under the curve is 1. So if you want to know, for example, what fraction of the molecules have speeds between V1 and V2. So let's say this is V1, 500, and V2 is 1,000, okay, meters per second. If I want to know what fraction of molecules have speeds between V1 and V2, I figure out this area right here. So that would be the fraction of the molecules that would have that much speed between V1, 500, and 1,000 meters per second. The total area under this curve is 1, okay? So this particular curve is for oxygen at room temperature. Okay, so this is for oxygen at 298 Kelvin. This is the function. So that's called the speed distribution function. Okay, before we go to the next line, let me show you an animation that illustrates this. Here's a website, www.chm.davidson.edu/VCE/Kinetic Molecular Theory/Maxwell.html. Okay, here's an animation that shows the molecules at 100 Kelvin. So if you give it enough time, you get here the distribution of the speeds. You'll notice this bar. This is a bar graph. It tells you how many molecules have a particular speed in this particular sample. Okay. Now, what would happen if you were to raise the temperature to, let's say, 500 K? You know that they're going to speed up, right? The average speed is going to increase, and you'll notice, okay, at 500 Kelvin, give it time to settle down, and you'll notice you got more molecules. See, this is higher speed over on this side. Okay, you get more molecules that are able to achieve higher speeds at higher temperature. Okay, so the temperature of your gas is indicative of the average speed, but So the higher the temperature, the speed, higher the average speed increases. That simply means that you have more molecules that are able to achieve higher kinetic energies, higher speeds. So let's take a look at this question right here. The molecular distributions for the same gas sample at two different temperatures, T1 and T2, is shown in this figure below. Okay, so this is T1, this is the blue curve right here is the distribution at T1, and the red curve is the distribution at T2. Which distribution corresponds to a higher temperature? Well, at T1, you get more molecules able to reach higher speeds, right? So T1 corresponds to a higher temperature. How about this one? This is speed distribution for helium and oxygen at the same temperature. Which one do you think represents helium, A or B? What did we say? Remember temperature, okay? They have the same temperature, right? That means you're looking at the same average translational kinetic energy. If you have the same average translational kinetic energy, same temperature, okay, which one will be moving faster? What's the formula for kinetic energy? 1/2 mv squared, right? So, what's the difference between helium and oxygen? If you're looking at the same kinetic energy, let's just compare the average helium molecule and the average oxygen molecule. If you have the same kinetic energy, the higher the mass, the slower the speed would have to be. Okay? So in other words, for an atom of helium and a molecule of oxygen, if they have the same translational kinetic energy, the heavier one will be moving more slowly. So oxygen molecules would move more slowly at the same temperature on average compared to helium atoms. So that means this curve right here, A, these are slower moving particles, right? So this would be the heavier atoms, heavier molecules, heavier particles. So this will be your O2, and B would represent your helium. So this would be the faster moving. They have the same average translational kinetic energy, but their speeds, the average speeds, are not the same. The heavier particles would be moving at slower speeds for the same amount of translational kinetic energy. Now let's talk about diffusion and effusion. Diffusion simply refers to the spreading out of a gas, and that happens because your molecules are always moving, right? So if you give them room, they'll fill up the entire room. Effusion refers to the movement of a gas sample through a pinhole into a vacuum. So imagine you have a container, you punch a little pinhole there, so you have a gas here. On the other side, you pull a vacuum. Okay, so you pump it out, pump out all the molecules, so you have a vacuum there. So the movement of your gas through that pinhole is called effusion. Now the rate at which effusion occurs depends on the concentration of the gas molecules in your sample. Okay? Why is that? The more crowded they are, the higher the concentration, the more frequently they're gonna hit that hole right there and be able to leave. So the higher the concentration, the faster the rate of effusion. It also depends on their average speed. Why? The faster they're moving, the more frequently they're going to collide with the wall, the more frequently that you'll have a molecule end up hitting that hole in the wall and leaving your chamber, your gas chamber. Okay? It also depends on the area of the pinhole. The larger the area of the pinhole, the more molecules are able to pass through. So the rate of diffusion depends on these three factors. And number of moles divided by the volume, that's a concentration. If you look at the ideal gas law, N over V is just P over RT, so that's P over RT right there. The average speed we showed earlier is square root of 8 RT over pi m, and then there's the area right there. Okay, so that would be the rate of diffusion out of a chamber. Now, if you look at this expression right here, you can see at the same conditions, if you're looking at the same chamber, okay, same pressure, same temperature, same pinhole, okay, then if you put different gases in there, then the rate of diffusion of the gas will be directly proportional, same temperature is going to be inversely proportional to the square root of the molar mass. If everything is the same, okay, same temperature, same pressure, same chamber, okay, same area of pinhole, okay, the rate of diffusion is inversely proportional to the square root of the molar mass. The bigger this molar mass, the slower the speeds, remember? Okay, so the slower the rate of diffusion. So you can say, remember we say if two things are inversely proportional, then their product must be a constant. So the rate of diffusion of gas 1 times the square root of the molar mass of gas 1 will be equal to the rate of diffusion of gas 2 times the square root of the molar mass of gas 2. Or if you square both sides of this equation, you can say R1 squared M1 equals R2 squared M2. All right. What's the application of this equation? This tells us that if we have such a chamber and we measure the rate of diffusion of one particular gas, okay, with a known molar mass, and then you put an unknown gas in there and measure the rate of diffusion of that unknown gas, you can figure out the molar mass of the unknown gas. Right, so let's apply that to this question right here. This is about diffusion. Cotton balls dipped in concentrated aqueous solutions of ammonia and HCl are simultaneously placed in opposite ends of a glass tube. So let's say you have a glass tube here. So you have a cotton ball over here with HCl in it, and a cotton ball over here with ammonia in it. Okay. What will happen is your ammonia gas is going to diffuse. So this is going to be a diffusion into your tube, and your HCl gas is also going to diffuse into the tube. When they meet, okay, your ammonia will react with HCl. So both of these are gases. When they meet, they're going to form a solid of ammonium chloride. And you'll see a ring inside this tube, okay, where they meet. The question is, where will you expect this ring to form? Is it going to be closer to the ammonia, or is it going to be closer to the HCl end of your tube, or is it going to be exactly halfway? To answer this question, you need to compare the rate of diffusion of ammonia and HCl. Which molecules will move faster? We're talking basically the same temperature, same kinetic energy. So you compare the average speed. Well, how's the average speed related to the molar mass? Average speed is what? Inversely proportional to the square root of the molar mass, right? So what are the molar masses? NH3, so nitrogen is 14, hydrogen is 1 times 3, so that's about 17 grams per mole, 17 AMU. The mass of one ammonia molecule. HCl, hydrogen's 1, chlorine's 35.5, so that's about 36. So which one's heavier? HCl would be heavier, right? More massive. So at the same temperature, these HCl molecules are going to be slower than the ammonia molecules. So which one will get to travel further? They're going to meet somewhere over here, closer to the HCl. The ammonia molecules will be able to travel farther because they'll be faster compared to the HCl molecule. So it's going to be closer to the HCl end of the tube. There's actually a YouTube video that shows this. I did this experiment in high school. Let me see if I can find that YouTube video for you. So if you go to YouTube, oops. Let's do a search for NH3HCl reaction right here. Diffusion of NH3 and HCl. Just do a search for that. This is really nice animation from North Carolina School for Science and Math. So here's the tube right here. Okay, and so on this tube, and you have on both ends, on each end of the tube, one you put HCl on one end and ammonia on the other end. And if you watch this video, you'll see where the two will meet and will form a ring of ammonium chloride. Okay? Alright. Let's look at an application of the rate of diffusion. By the way, that's known that the expression that says the rate of diffusion is inversely proportional to the square root of the molar mass. This relationship is known as Graham's law of diffusion. Before I forget to mention that. Graham's law of diffusion. Okay. The rate of diffusion of a gas is inversely proportional to the square root of its molar mass. Alright, so let's look at this problem right here. Carbon dioxide diffuses at a rate of 2 millimoles per minute. At the same conditions, an unknown gas diffuses at a rate of 3.32 millimoles per minute. What's the possible identity of the unknown gas? Well, you use R1 squared of M1, R1 squared. Let's do the squared version. So you're going to say R1 squared times M1 equals R2 squared times M2. Okay, so M2 is our unknown. So let's solve for M2. M2 equals R1 squared M1 over R2 squared. So R1 is carbon dioxide. It's 2.0 millimoles per minute. And the unknown gas is 3.32 millimoles per minute. And you square this, because R1 and R2 are both squared. And then M1, what's the molar mass of CO2? Carbon's 12.011. Oxygen is 16.00 times 2. I did this, you see 44.01 grams per mole. So our molar mass for gas number 1, which is carbon dioxide, is 44.01 grams per mole. So let's calculate that. 2 divided by 3.32, that's 0.6. We square that, that's 0.36 times 44.01 equals 15.97. 3 sig figs, that's 16.0 grams per mole. So which one is it? And just compare, just figure out the molar masses of these, all right? So, what would it be? Methane, that's carbon is 12, hydrogen is 1, 1 times 4 is 4, so that's about 16. That looks like it's going to be methane. Okay. Oxygen would be 32, chlorine is 35.5 times 2, so that's going to be about 71. Carbon tetrachloride, that's 12 plus 4 times 35.5, so obviously it's not that. So our correct answer is A, methane. How much faster would helium effuse compared to CH4 under the same conditions? So let's compare the rate of diffusion. So we say R1 square root of M1 equals R2 square root of M2. So we're going to call CH4 our gas number 1, and we're going to call helium our gas number 2. So if you want to compare, we're going to say R2 over R1, the rate of helium over the rate of methane. Okay. Of course, we know helium is going to effuse faster, right? Because it's lighter. So that's going to be equal to R2 over R1 is square root of M1 over square root of M2. So that's square root of M1 over M2. So that's square root of molar mass of number 1 is methane, so that's 16 approximately. If you want to do it exactly, more precisely, carbon's 12.01, hydrogen is 1.008 times 4, so that's 16.03, okay? 2. And helium would be 4.003, you can look it up on the periodic table. So that gives you 16.032 divided by 4, 4.008, you take the square root, so raised to the power of 0.5, that gives you 2.00. That means helium will effuse at a rate that's 2 times faster than CH4. As expected, helium is lighter than CH4. Under the same conditions, it will effuse faster. Okay. By the way, back here, let's check if our answers are reasonable. Carbon dioxide effuses at a rate of 2. The unknown gas effuses faster, right? So you know your unknown gas must be less than 44 grams per mole. Less than the molar mass. The molar mass of your unknown gas has to be less than that of CO2. So right away you could eliminate chlorine and carbon tetrachloride. So if you have no idea, you can reduce your choices to 50-50. Cans. All right, that's one final example here. Consider a gas containing 0.7% uranium hexafluoride with a uranium-235 isotope and 99.3% uranium hexafluoride with a uranium-238 isotope. So this would be the heavier gas, right? This is the lighter gas. Lighter. If the gas is confined in chamber A and is allowed to escape through a pinhole into a vacuum, chamber B, the percentage of uranium hexafluoride with the 235 isotope, so this is the lighter isotope, that initially emerges in chamber B will be higher than 0.7%, lower than 0.7%, or it's still going to be 0.7%. Let's see, which one effuses faster? The lighter will effuse faster, right? So uranium-35 will effuse faster, so what comes out here is enriched, we say, with the lighter isotope, which would be uranium-235 hexafluoride. So that means the percentage of your uranium hexafluoride with the uranium-235 isotope is going to be higher than 0.7%. Okay, so this is uranium, this is the principle behind the enrichment of uranium-235. Okay, and that's it.